Yep.
Especially those ends.
So, any questions? Any questions at all? I have some quizzes for a few people. No questions on sapling?
Well, yeah.
All right, give me the gist of the question. Ah.
Which two are in equilibrium?
I'd have to look at the question. Oh, what rookie left the pen out? Gonna have to raise tuition. All right. Jason, go grab some markers. Yeah. Here, in case Audra's not there. Go grab like three black markers. All right, equilibrium. One thing that we didn't really go over too much, and that question might lead into it. But if you get to this, okay, so we're talking about a chair. Okay, I got better markers coming. So a chair flipping its conformation to another chair, okay? So, okay, that was horrible. I'm not as good at this chair. There we go, better. All right. And, all right, thank you.
Both bad?
What's that?
Both bad.
Those are, yeah, throw them away. Thank you. So, that carbon, we'll call that one 1, and we'll call this one 4, okay? This is actually carbon 1, and this is carbon 4. So we didn't just flip it over or rotate it. We actually rotated bonds. Okay. Well, the way in which it gets there is on an energy diagram. So this might be kind of what that question was talking about, possibly. If not, pull it up and we'll see if we can figure it out. So I don't have any axial or equatorial groups on there, so both of those have the same energy. Okay, so those are, both have the same energy, and because they're all hydrogens, it would be a 50-50 mixture of the two. So you ask me, well, how would you ever find out if it's a 50-50 mixture, right? Well, there are instruments that we could use that would look at the hydrogens, the axial and equatorial hydrogens, and they would be different. Okay, and so we're going to talk about those instruments in a few weeks. But you can tell the difference between those two. Okay, or you could label it in some way. You could put a deuterium instead of a hydrogen here, or I could, if you wanted to, you could put a fluorine there and then do that comparison. So there's ways in which you can determine this. Actually, do the experiment and determine it. But this goes up through an energy barrier, okay, and then comes down to another energy minimum. So if this is the lowest energy, what are we going to call it? Global minimum, right? So this is the global minimum, and this would be a local minimum because it's still in an energy well, okay? And then there's a little bit of a bump and it comes down to another one and then up and over and down to this, okay? And these are all, this one's all symmetrical. If I were to put a group on here, if I put a methyl group on here, it wouldn't be symmetrical anymore. That looks pretty symmetrical. So anyways, they're really hard to draw, but we call this one the twist boat, B-O-A-T. This was a maximum. That's boat, but it's I try to make this one look higher. Okay, does that one look higher? So if we were to do the maximums, these are going to be the global max, right? And those should be, and this is a local max. Okay, so the boat is a local max. And then these are hard to draw, but these up here are called a half chair. Okay, so the boat conformation is, so if I were to draw the boat here, it looks kind of like that, okay? So it looks like so you just, both ends are flipped up, basically. So you get there by just flipping one of the ends up. The twist boat is that, but you twist it. So if you were to take your models, I didn't bring the models in today for you guys, but if you look at this big old model here, so that's the chair. The boat is like this, but the boat has everything eclipsed still, okay? So it has all the hydrogens are eclipsed, but if you just twist it a little bit, so there's the boat, you can see the hydrogens are mainly eclipsed. If I just give it a little twist, then that goes into a minimum. It's not the global minimum, it's just a local minimum, okay? And then it just kind of gets those hydrogens a little bit more skewed from each other, okay? Does that make sense? So the half chair is really, it's flat on one side and up. It's basically flat on one side and a boat on the other, and it's really hard to draw. So I would never ask you to draw that on an exam because I wouldn't be able to interpret what you said, probably what you drew anyways. Yes?
There was another sapling question regarding the chair stuff, and it said, like, when you're looking at it, how can you know which ones are gouged to each other?
Oh, okay, that's a good question. We'll just go right by that one. What was your question? I'll come back.
Why does the half chair higher energy than the twist boat?
You'd have to get the models and look, but basically it eclipses more hydrogens. If you do the twist, it uneclipses some hydrogens. So yeah, if you get the model, if you want to grab one of the model kits, like tomorrow in lab, I can bring model kits in. We can mess with the model kits while we're waiting for TLCs to run.
And that one has a methyl group, so it's not the super even.
Right, this one,
Right.
yeah, that's, yeah, so that would be, if I had a hydrogen on there.
Out the methyl group.
Right, so with the methyl group then, so if I come over here, let's say I have you do this, but I say, hey, methyl cyclohexane. Well, that's going to be really hard to figure out which half chair is going to be higher in energy and which twist boat and which boat and how that's going to be really hard to do. Okay? But you should be able to tell me which one is higher in energy between this one and this one. Okay, so this one is going to be higher in energy. So so it makes it unsymmetrical, and these are going to change as well. So I don't know, that one might be higher Maybe this one is higher. Maybe, but we could try to model that and figure it out. But definitely the two cyclohexanes, the one with an axial group is going to be at a higher energy. Okay? So I'll get back to the Newman structures of these. So I'm going to draw it this way because I'm better at drawing it. So if I have, now I can use wedges and dashes there because it's not on the ring. Okay? So that actually does, it's going to rotate and it's actually going to go back and forth. Okay? But wedges and dashes off the ring, we don't want to do that. So the question here is, why? So not only that it is, that an axial group is less stable, but why is it less stable? And you want to get all the points for that question, right? That's going to be on the exam, possibly on the quiz. So why? Or are you waiting for me to answer my question?
I don't know what you're asking. Is it the bonding rules? Or is it something else?
There's one phrase answer that's going to get you all the points. Steric hindrance. Okay, that's definitely because of steric hindrance. Steric hindrance to what? So definitely steric hindrance would be a good one-word answer to get all the points. To get all the points, especially if I say draw. Oh, I could have drawn this a little bit better here. I'll redraw this a little bit better. So this is, if I call that carbon 1, 2 away from that one is 3. And if I count the other way, 2 away from that one is 3. And this is where the hindrance comes. It's between those other axial hydrogens. So the best answer is, the reason why axial is less stable is because of 1,3 diaxial repulsion. Yes?
Could you also call it diaxial interactions? Would that be correct?
Maybe like a 9 out of 10.
Okay. I'm just asking because that's what the textbook says.
Sure, I give you full credit, especially if the textbook says it. Probably it's just my textbook in 1975, no, I was not that old, but had repulsions. So yeah, interactions. 1,3 diaxial, I don't know, repulsion is probably not a word that is good anymore, right? I mean, it's probably gone out of style. You know, so you have an ex-boyfriend, girlfriend, it's repulsive. So, it's probably a word that's gone out of style. So I'll go with interaction. I don't want any more 1,3 diaxial interactions with my ex-girlfriend. So, she's repulsive. Okay. I'd like to see the specific on the Newman structure, but if you can draw a Newman structure of a ring as well. So that's the Newman structure of a cyclohexane looking right down the front. Okay? So I didn't put the hydrogens on there, but here, if you're going to look right down this carbon to this carbon, this carbon to this carbon, one of them goes up, one of them goes down, right? So I drew this one with it down. So I've been showing you a ring like this. If I twist it to you like this, just rotate it and put these two groups in the same plane. That's what this Newman structure is saying here, and I have a CH2 and a CH2 there. Then you can put in the rest, so all the hydrogens just match up to this, just the same. So there are my two hydrogens. There are my two hydrogens. Here, I would be okay to say coming forward and going back because it's no longer a chair. And so all of those hydrogens, looking at that, are going to be staggered from each other. But if I put a group on, maybe this is what it's asking. If I put a group on, like there, then that is gauche to this hydrogen. Or if I had another one on here, that would be gauche.
This is what it looks like.
Okay. What is the... oh, this is technology at its best right here. All right. Given the cyclohexane framework, chair confirmation, label each position as axial equatorial. Okay, did that. On the same figure, label all positions that are gauche to each other to the Y group. So,
It's the second set question you were checking.
so both those hydrogens are going to be gauche. So on the adjacent carbons, just on the adjacent carbons. So gauche means, so if I have just butane, let's say, we're good at saying, well, those things are gauche of each other, okay? But gauche, that's because we're describing the methyl groups, but actually everything that is just 60 degrees off is gauche. So this hydrogen is gauche to that methyl group. This hydrogen is gauche to that hydrogen. It just means left or right.
Yeah.
But the French always go
So it's
counterclockwise. So
the
it's
bonds directly connected.
right connected to it, and then you've got, if you look, you've got,
Up one and the down.
and the down one. They're both gauche. Yes.
Very simple question. Just the dashed versus the wedge. Which is which? Because Sapling told me both, and I missed one. Because it said like the wedge is coming out, and then the other one it said the wedge is going back. So I was just confused because it told me both, and then I missed one because of it. So I was like, what? Okay.
Wedge is coming forward, dash is going back.
Cool.
Okay? Wedge is coming forward, dash is going back. If Sapling made an error, that happens.
It's not a big deal. I just
Yeah.
confused.
You just want to, the wedge is coming forward.
Okay.
So, do you guys know the study that Georgia Tech did, where they had Georgia Tech's huge, right? So they have 150 sections of English, English 101. Okay, because you got to break that up, and so they have tutors assigned to each section to help students with their writing. And they don't necessarily meet; they just email each other, and the tutors are supposed to get back to them, and et cetera, et cetera. So Georgia Tech, is also a tech. So they created a robot, an artificial intelligence robot that would interact with the students and correct their papers, tell them where to put commas, all that kind of stuff. And they just inserted, I think her name was Alice. They made it a girl. Her name was Alice. Is that right? Did I get it right?
Yeah. John took AI from Georgia Tech, and he was talking all about Alice.
Okay. I got it right. I got it. Oh, that's right. That's your brother, right?
Yeah, John. Yeah, he's getting his master's in computer
I forgot.
science from Georgia Tech.
I forgot that. Okay, yeah. So they created Alice that goes and grades, helps students with their writing. And then, like you'll do, you give course evaluations out. And so they evaluated all the TAs. Alice gets the top awards for being the best TA. Okay, she is the best. Well, for one, you're dealing with sentence structure and things that an AI can do. And the other one is that Alice never sleeps. Alice will answer your question at 2 in the morning and get back to you at 2:05. All that kind of stuff. So, but when you get to things, this is why I haven't done. Online homework's been around for a long time, but I've not done it until the last about 3 or 4, maybe 5 years. I've done online because it was just horrible. Still find some issues. If you want to screenshot that to me, I'll send it to Sapling and they'll correct it, because that's how because they want to get it right. I had one where a student couldn't get a problem, and she was in my office, and we ran through the entire thing. It was on the next chapter, stereochemistry, and we ran through the entire thing, and I had it right. I had it right. I knew what I was doing, and I hit, the answer button, and it marked every single one that I had wrong. And I'm like, this is ridiculous. And so, turns out the way in which you started the problem mattered. So if you started it one way and did what you're supposed to do, you got it all right. If you started it the other way and did what you're supposed to do, you got everything wrong. And so I emailed that to them, and they're like, oh yeah, I guess that's a problem. So yeah.
Newman of like a ring, does it matter which bond you look down, like if there's like a methyl or something?
So just what you want to describe. So they get kind of complex pretty fast, but so a Newman structure, you would say, give me all the Newman structures of butane looking down the 2,3 bond. Okay, because those are going to be the ones that are important. I'm not going to ask you a lot of Newman structures about cyclohexanes. It gets complex pretty fast. No question. Stretching. Okay. All right. All right, that's a good question. Any other questions? We're good? We are going to go over everything today. Was that section 4? All right, so I'm going to ask you some questions. My notes.
I stole them.
They're online, but you don't have to print them out if you steal mine. All right. Oops. Okay, put those two structures in their most stable form. That's going to be a question. Put those two structures in their most stable form. Most stable conformation, I should say. Conformation. So we got a choice. We can do a boat. We could do flat. We could do twist boat. We could do skewed boat. That's twist boat. We could do half chair. Which one do we want to do? Okay, we want to start off with a chair. Okay, you guys got them? No cheating, Allie. No, she was. She looked right over at your paper. I got you both, though, right? Allie. All right. Anybody want to give me a... We're going to do a chair. Okay. And then I just start off by putting a group out there. So I'm going to take this, I'm going to say this is carbon 1, carbon 2, carbon 3. I'm just going to, you can make any carbon you want 1, 2, and 3. It doesn't matter. I'm going to say this is 1, this is 2, and this is 3. You could go 1, 2, 3 over here. Okay, you number them either way. I'm going to put this one equatorial. Okay. So I'm going to put it on this carbon. So I'm going to say, okay, if it's cis, equatorial, axial, equatorial, but it is trans, so it's axial. How did I know that? What was the question?
How do you know it's axial? You walk around the ring. Okay, so here's the methyl group. See how so believe it or not, this, if I put this flat, this okay, so if I put this flat, would you agree that this methyl group and this hydrogen are on the same side of the ring? So that would make them cis, right? So we're looking at this hydrogen. So did I get it wrong? Did I get it backwards? 1, 2, 3. Hold on, maybe I got it wrong. Good question, maybe I got it wrong. Axial, equatorial. Oh, am I looking at the wrong one here? 1, 2, 3. Oh, shouldn't matter. So if it's flat, I think I'm right. I don't know how I can show you on this. Oh, I think I am, okay. One, two, three. Okay, I am flipping it the wrong way. That's what I'm doing. So my problem is this should be over here if I'm doing that this way. So if I put that equatorial,
then this, okay, so this one, let's get this flat again. So my problem is this is net axial, and I have it equatorial up there. So I'm going to take, so if I do that, then I got to flip this over. This is,
Flip the ring upside down.
there we go. Now I got to do that. Hey, thank you, Jason. So, okay, so here you would say that hydrogen and that hydrogen are both axial, right? And this one's equatorial. Okay, so this one, so now this looking at this one and this, those are trans from each other. So this hydrogen and this methyl are trans from each other because this one is in the bottom half of the ring, this one's in the top half of the ring. So that's why I put this one as axial. So find your way of doing it. So find your way of doing it, and if you want to walk around the ring differently than that, it's okay. It's just that's the way you do it.
Do you always start out equatorial?
I do. You don't have to.
Or is it right or wrong either way? Or is there not?
Well, let's do the ring flip. Okay, we're going to do the ring flip now. Oh gosh, I'm so bad at these. Okay, so let's do the ring flip. Now this is down here, okay, and this is here. What's the difference in energy between those two? Think the second one's higher? No. What's the energy difference between those two? I got an axial methyl group and an equatorial. I got an axial methyl group and an equatorial. No. I've just drawn it that way. It's anywhere in there. So yeah, Allie, you could have drawn this one. What you cannot draw, so what is wrong is this one. That is wrong. This is wrong. That's wrong for two reasons. One is it doesn't go that way, and the other one is it's 1, 2. So those are all wrong.
Where would you put it if you were to number it the opposite way on that one? Where would you put the second?
Here on this one?
No, on the other one.
Okay, let me do this. So I got to go 1, 2, there. And now I got to draw another one. That's a little bit better. So I flip this down to here, and then this one becomes this one. There. Yeah, all 4 of those structures are correct. There are probably 6 more structures that are correct. But that relative stereochemistry has to stay the same. Yeah.
So just to clarify, so for the top one, with the cyclohexane, when we have one coming towards us, one going behind, as long as they are on opposite sides of the ring, so one has to be axial, one has to be equatorial, then it's a correct structure on the correct carbons.
I don't know if I can answer that question. Because usually when you say always, okay, you got to...
So like with your first 2 top drawings, one's equatorial, one's axial, and they're 3 carbons away from each other.
Right. you want to memorize all those rules? So if they're 2 carbons away from each other, or they're 4 carbons away from each other, or do you want to memorize all the various rules that there are that would give you all the cis and trans isomers?
No. I'm
No.
just asking, so like for the second one, with the bromine and the tert-butyl, you'd want those to be on the same side of the ring, but the methyl would be on a different side of the ring?
Well, we're going to find out. We're going to find out. I don't know the answer. Okay. All right. Did you guys do this one already? Okay, so here, remember I said that I went down into the basement and I figured this out. It's what you got to do. You got to come up with a way in which this works for you every time. Okay, because it just. Not everybody rides a bike exactly the same. Not everybody starts their pedals off exactly the same, holds the handlebars exactly the same. You got to learn how it's going to work for you, okay? And if you keep falling, so you start the bike and boom, you fall. You start the bike and boom, then you're not doing it right. So don't do it that way, okay? But if you're getting them right on sapling, then it's okay. So here, what's the largest group? The tert-butyl. So I'm going to put the tert-butyl right there. Now, could I put the tert-butyl anywhere else? Yes. Could I put the tert-butyl axial?
No.
I could. It's just that if I ask the question, what's the most stable conformation, then I would have to do a ring flip and draw it again. It's not wrong. It's the right stereochemistry. It's just not the most stable conformation. Okay? All right, so I'm just going to number this way. 1, 2, 3, 4. Okay? I'm going to number this way. 1, 2, 3, 4. So carbon 2, it's equatorial, and so this is going to say it's axial. So then axial, equatorial, axial. Hold on, I got to start over. Equatorial, axial, equatorial, axial. So it's equatorial. Do you guys get that one? I think that's right. Pretty sure. And that would be the most stable conformation because I've got the largest group going equatorial. Okay? Yes?
Can you explain why the bromine group is axial?
I'm not sure. Let me see if I'll flip it over. So, do you agree this is equatorial? That's the tert-butyl.
Yes.
This group right here is going to be cis. It's axial.
Gotcha.
Okay. These are fun. Look how much fun this is. Right? Does it? So I'm going to give you a little quiz on. We're going to do a couple quizzes, but I should have had a quiz today. I should have had the clickers. So we have some terms that we've used. So. That's one word. Okay, so I got 3 terms. I should have brought my my clicker. 1, 2, 3. Okay? So you're going to hold up a finger. 1, 2, 3. Okay, and I'm going to ask you a couple questions. All right? What's the relationship between these two molecules? Between molecule A and molecule B. What's the relationship between molecule A and molecule B? Raise your hand. Raise your hand high. You guys are looking around the room. Be confident. You're looking around the room. Come on. You're going with 3? He's strong with 3.
You said be confident.
Be confident. I'm good. I'm good. I got a 2. I got a 2. I got a people that are not participating. Back in the back here. What? What are we doing here? Okay. So to get from A to B, all we did were we rotated bonds. So that is a conformational isomer. It's a different conformation. Okay? I guess the other one is same molecule. I could do same molecule. That would be a conformation. Okay? What is the difference between these two molecules? What's the difference between these two molecules, A and B? Are they constitutional isomers? Are they conformational isomers? Are they stereoisomers? You're going with 1. I got a 3. I got a 3. I got a 2. Okay, so basically we don't know. Okay, A and B are stereoisomers. One is cis and one is trans. The difference between those two is there's still, if we were to name this molecule, it would be 1,2 or 1,3 dimethyl cyclohexane, right? And if I name that one, it would be 1,3 dimethyl cyclohexane, right? So they have the same name. So we have to add the stereochemistry to it. One of them's cis, one of them's trans. So the name would actually be cis 1,3 dimethyl cyclohexane and trans 1,3 dimethyl cyclohexane. Okay? Yes?
So conformational is atom connectivity, but stereoisomers is like their spatial arrangement.
Arrangement in space. Yes. Like your stereo has a left and a right. All right, how about this A and B? Are they constitutional isomers, conformational isomers, or stereoisomers? I got a 1, I got a 1, I got some 2s. Got some 2s, no 3s. Get some 3s. Okay, how about, see if I can do this on you. Okay, so the relationship between oh, hold on. There we go. A and B, one of them's name is 1,2 dimethyl, and the other one's name is 1,3 dimethyl. So those are definitely constitutional isomers of each other. Okay? Because they have different carbon-carbon connectivity. All right? What about B and C? Stereoisomers. One's cis and one's trans. What about A and C? Is A and C, are they stereoisomers of each other? No, because you have to be the same carbon makeup to be a stereoisomer. You have to be the same isomer. So those are constitutional isomers. Okay. All right. You guys are somewhat passing that, I suppose. All right. Okay, so I can add a fourth one on there. I could add a fourth one on there, which is same molecule. If you think this is confusing, wait till chapter 4. Chapter 4 will blow your mind. Chapter 4 is just going to like change the world for you. All right, so we got some fused rings here. Okay. So actually, if this one's trans, it's easy to draw. So this is transdecalan. And you just keep adding on these rings. So this one ends up being like this. Oop, pretty close. Okay. You can also have cisdecalan. This one's a little bit harder to draw. Something like that. 1, 2. It's on there somewhere. Let's not worry about it too much. Okay. But we have a whole new naming system for these types of rings. Okay. This is, you guys groaned, but it's like someone asked me, are we going to do this? And I said yes. So we have a whole new naming system for this. Okay. And what you do is you look at the ring juncture. So you look at those two carbons there, and you count how many carbons are over here, and you count how many carbons are over here, and you count how many carbons are in between. And you call this, so this one here would be bicyclo 4,4,0, and then you say, how many total carbons do I have? And I have 10, so you say decane. Okay? 4 carbons here, 4 carbons there, and no carbons in between.
Oh.
Okay? Okay, we got that one. We got that one. What time is it? That one. Okay. So is this a bicyclo? So this one is bicyclo. Yeah, that's the thing, because they mess with us. It's 4, 1, 0 heptane. If you have a bicyclo, you have to have 3 numbers. Okay, let's do this one. Bicyclo.
Does the other one have 2 line? Cross bridge.
Yeah, that. It's got to go behind. It's hard to draw that. It goes behind it there. So. 2, 2, 2. 2, 4, 6, 8. Okay. This one is bicyclo. Three, 2, 1, 2, 4, 5, 6, 7, 8. Octane. See how that works? No? So it's a bicyclo because I have a fused ring. So anytime you have a fused ring, so that's 2 carbons in the same ring. Here I have a fused ring, but it's not fused on the side. Like this one's fused on the side. This one's fused as a bridge. Okay? So what you do is you say, well, first of all, you say how many total carbons there are. So there's 7 total carbons there. So it's going to be a heptane. 8 total carbons there, so it's going to be an octane. And then you say it's bicyclo. And then you say how many carbons are in each chain of the ring. So here I have 4. Here I have 1. And here I have 0. So it's 4, 1, 0. I'll get to you. Here I have 2, 2, 2. So it's 2, 2, 2. Here I have 3, 2, 1, and you put the big number first, except for the next one. I don't know why. Okay, we got that now? Your question?
Well, yeah, the bridge, you put the small.
You put this. You number it 3, the smaller one first. Okay. This one is not a bicyclo. This one is a spiro. And it's still a heptane. So what's the spiro on this one? 3, 2, right?
It's 4.
4, 2, right? So I don't know why, and I won't mark you wrong for this, but this one is 2, 4.
You will mark this one?
I will not mark you wrong for it, but Sapling will. Yes.
So is the reason why it's the spiral instead of bicycle because it's not actually touching each other?
Coming off the same carbon.
Okay.
If they're coming off the same carbon, it's spiro. If it's coming off of 2 different carbons, it's bicyclo.
Okay.
All right.